Hi, Assalamualaikum everyone. This video is about chapter 5, frequency response and Bode plot part 1. Okay, so here are the outlines of this video. I'm going to tell you about the filters, the introduction of filters, the type of filters, and how ideal and practical filters look like. And then just a brief introduction about the Bode plot and how to generate the transfer function as well as frequency response plot. So it is actually a special network purposely designed to block unwanted frequencies. Okay, we've learned some of the filters before in the Fourier transform chapter. Okay, so we know that filter can remove the frequency that we do not want and can retain the frequencies that we want. So a filter is typically designed to pass and stop some frequency regions. Because if you see at the simple communication system here, where we have transmitter and the transmitter is being modulated to become a high frequency signal, for example a cosine omega t, and this high frequency signal, when it is being transmitted through the free space, there will be noise added to the signal, and this noise at the receiver will be added as a cosine omega t plus nt. This noise is nt. And then this is where we need filter because we want to remove the noise. Okay, this is the first part of filter. We want to remove the noise and we want to retain the original transmitted signal, which is a cosine omega t. So moving forward to the right hand side of the system, which is not included here, there will be many more filters to remove the upper frequencies during the demodulation process. Okay, so basically we know that filter is designed to remove the unwanted frequencies and to retain the frequencies that we want. Okay, there are actually many types of filter, and for this lesson for signal and system, we are going to learn about passive filter network. Okay, passive filter network consists of passive elements such as inductor, capacitor, and also resistor. These are called passive elements. Okay, meanwhile, active filter network consists of active elements such as op-amp and transistor. So I believe you will learn, or you have learned this in the electronic subject. So our discussions are limited only on passive filters. Okay, so the basic diagram of the filter, in which we have input and we have the combination of inductor, resistor, and also capacitor to form passive filters, and finally we have output. Okay, and in the next chapter, which is chapter 6, you are going to learn how to construct this passive filter network using the inductor, capacitor, and resistor. So recall some of the terms that we have seen before in the Fourier transform. The frequency range over which the output is significantly attenuated is called stop band. Okay, attenuated means that the output or the signal is weakened. Okay, dia makin lemah and makin slow. Okay, in other words, the amplitude becomes lower and lower. So when that happens, we call it stop band. Okay, within that frequency range, we call it stop band. And then the frequency range over which there is little attenuation is called pass band. Okay, it means that during the pass band range, there will be a little attenuation. The signal will be weakened a little. Okay, but then it can still go through that frequency range. The cutoff frequency omega c is defined as the boundary between pass band and stop band. Okay, basically the cutoff frequency is the frequency that determine whether the frequency after that, okay, or before that, can go through that range or not. Okay, so that is a cutoff frequency. Okay, this is how ideal filter looks like. Okay, we can see that there is a sharp cutoff frequency here. It means that sharp at omega c. After omega c here, any signal with frequency above omega c will be stopped. Okay, cannot go through this filter. Okay, and only frequency between 0 to omega c here can go through this filter, in which we call this range as pass band, and this is stop band. Okay, and here we call it gain of the filter. Okay, it means that how much the signal can be increased in terms of amplitude, or maybe retain the same value as it goes through the filter. Okay, and also for this chapter, okay, you are also introduced to phase. Okay, phase for the filter. Okay, so in terms of the phase, we can see that there is a linear phase change for the ideal filter. Okay, there is a linear. Okay, because this is ideal, which corresponds to the sharp cut-off frequency here. Okay, we will see later on in the second part of this chapter how we can plot this ideal filter, and also the phase, okay, through the Bode plot. Right. On the other hand, for the practical filter, we can see the transition for a gradual transition from pass band to stop band. Okay, there is no sharp edges. Okay, tak ada bucu yang tajam here. Okay, because the transition is gradual from pass band to stop band. Okay, the cutoff frequency is at which the gain has decreased by a factor of 0.707 from its maximum value pass band gain. Okay, so again, because of there is no sharp edges here, we define omega c. Okay, we define omega c at the intersection with the gain that has decreased by a factor of 0.707. Okay, so it means that by a factor of v divided by square root 2. Okay, if you find the value of 1 divided by square root 2, you know that it is going to be 0.707. So once the value of the gain here reduced to this value, okay, then the intersection of this filter we defined as omega c, which is a cut-off frequency. Okay, so in terms of power, if we define this as the power in dB, the cut-off frequency is at half the maximum power of negative 3 dB point. It means that this is the maximum power, and if it goes down to negative 3 dB point, then the intersection here is defined as omega c. Okay, so as we can see here, even though this is stop band, some of the frequencies that can that goes through this part, okay, can still go through because it is not sharp. Okay, but we define this as omega c. Okay, now we'll see at low pass filter. For the low pass filter, the frequency that can pass is less than omega c. Okay, so omega c is our cut-off frequency. Okay, any frequency that is less than omega c can go through this filter. It means that this filter only allow lower frequency. Ideal magnitude plot of low pass filter here showing pass band and stop band separated by cut-off frequency. The ideal one is the green one, which shows the sharp edges, and the non-ideal one is the red one, okay, which shows the gradual transition from pass band and stop band. Okay, so this is low pass filter. So for example, in the Bode plot, if you are required to plot a graph, and when you plot, the shape is like this, and you know right away that this is a low pass filter. Okay, the shape is just like the red color line here. Okay, and if the shape is like this, it means that it is high pass filter. So high pass filter, the frequency that can go through this high pass filter is any signal with frequency bigger than omega c, which omega c is the cutoff frequency here. Right? So the ideal magnitude plot of high pass filter is this green color showing the pass band and stop band separated by cutoff frequency. And this is the edges, okay, sharp edges to indicate the ideal high pass filter, and the red color here is the non-ideal high pass filter. Okay, so even though if we see the non-ideal high pass filter, any frequency which is less than omega c here still can go through this area, right? But this is not that much, okay, because it is a slow or attenuated signals already, okay, because when we see the high pass the line for the high pass filter here, okay, omega c here is defined when the signal is at 0.707 attenuated from the maximum gain, which is 1. Okay, so in other words, okay, there's a difference actually between non-ideal and ideal filter, but in real life when we want to implement the filter, you cannot have this ideal filter in which sharp at omega c only the signal can go through, after omega c only the signal can go through this filter. Okay. Alright, another one is band pass filter. Okay, band pass filter has the two cutoff frequency, and it can pass a range of frequencies between omega c1 and omega c2. Okay, we can see the ideal filter here, ideal magnetic plot in the blue color here, showing the band pass filter with pass band and stop band separated by two cutoff frequencies. Okay, so there will be two stop band. Okay, and the pass band is in between omega c1 and omega c2. And we can see the non-ideal shape, okay, gradual transition, and omega c is defined here as 0.707 from the ideal magnitude, or we can see 3 dB that goes down from the ideal magnitude. Okay, so this is cutoff frequency for the pass band. Okay, there will be two, and only the signal in between this cutoff frequency can go through this band pass filter. Okay, this is another type of filter, which is band stop filter. Okay, so this is opposite of band pass filter, because for band stop filter we have one stop band and two pass bands. Okay, if we remember the band pass filter, we have two stop band and one pass band. Okay, so for band stop filter, we the frequency range that can go through is from omega less than omega c1, which is the first cutoff frequency, and omega bigger than omega c2, which is the another cutoff frequency. So we can see that this is actually the combination of low pass filter and high pass filter. You can also see the non-ideal filter, okay, from this red color line here, which shown you the gradual transition from the pass band to stop band, and goes back up for gradual transition between stop band and pass band. Okay, now we want to know another term, which is the bandwidth of the filter. The bandwidth of the filter is defined as a range spanned by its pass band. It means that the range between omega c1 and also omega c2. Okay, for example, for band pass filter, the bandwidth is the difference in these two cutoff frequencies. So we can find it by subtracting omega c2 with omega c1. Okay, so this is the bandwidth of the filter. Okay, now I'm going to introduce a little bit about Bode plot, but we're going to learn about how to plot the Bode plot in another part of chapter 5. Okay, so first we need to know about the frequency response. For a circuit, a frequency response describes the relationships between the amplitudes and phase angles of the input and output sinusoids, which are frequency dependent. Okay, so in other words, it describes the relationship between the input and output in terms of amplitudes and phase angles. And Bode plot is a generalization of obtaining the frequency response of a network based on the transfer function. So I repeat, okay, it is a generalization of obtaining the frequency response of a network based on the transfer function. So this transfer functions is this relationship that we describe between the input and output sinusoids in terms of amplitudes and phase angle. And Bode plots allow us to approximate the frequency response of a circuit using straight line approximations and becomes the industrial standard method of presenting frequency response information. This is because when we want to plot frequency response, for example, if we want to plot frequency response against a very high range frequency, a very big or large frequency range, so we need a very large graph. Okay, so when we use Bode plot, okay, it will be generalized based on that frequency response, so we can somehow plot a larger frequency range in one graph. Okay, so the application of this Bode plot, okay, and also filter, we can see that most networks behave or act as filters, okay, because it can stop certain frequency or certain range, or okay, so many applications need to retain components in a given range of frequencies and discard the components in another range. Okay, so this can be accomplished by the use of electrical networks called filters. Okay, and when I talk about the relationship between the input output of a circuit, okay, it can be described by the transfer function, which is defined as the ratio of the phasor output voltage here to the phasor input voltage as a function of frequency. So we represent the transfer function as Hs equal to V out over V in. Okay, and magnitude of transfer function shows how the amplitude of each frequency component is affected by the network. Okay, there is magnitude of transfer function. On the other hand, the phase of transfer function shows how the phase of each frequency component is affected by the network. Okay, we can see the example here. Find the transfer function of the network below given as V2, okay, divided by V1. So this is a circuit. So we have to find the relationship between the V2 and V1, okay, using this R and also C. So V2 is the voltage across the C, okay, the capacitor, and V1 is the input voltage. Okay, so we can find the transfer function by voltage division. Okay, so remember that Hs is V2 over V1. Okay, so V2 over V1 Hs. Okay, so V2 is the voltage across the capacitor. Okay, so it is defined as 1 over SC, and V1 is R plus 1 SC. Okay, right, so we rearrange this so that it will become equal to 1 over SRC plus 1. So when simplify this, okay, simplify and solve for this, you can get 1 divided by SRC plus 1. Transform, so S here is actually equal to sigma plus j omega. However, at steady state, sigma is equal to 0. Okay, sigma is equal to 0 at steady state. Okay, so we can replace S here with j omega, and therefore the magnitude and angle of Hs now becomes, okay, so we replace S here with j omega, so it becomes Hj omega. Okay, so we will take this equation, it will be equal to 1 divided by 1 plus omega RC square. Okay, So how did we get this? How do we get this? Hj omega means that we want to find the magnitude of hj omega. Okay, so it's actually hj omega equal to the square root of 1 divided by, because 1 plus src here is actually 1 squared plus j omega rc squared. Okay, so you do this, okay, you will get 1 plus omega rc squared. Okay, and delta omega is the actually arctangent of omega rc. It's actually arctangent of omega rc divided by 1, so which is equivalent to omega rc. Okay, so w here is actually omega. Another example. So let's say here the transfer function for a network is already given as hs equal to this value. Okay, s multiplied by 10 power of 4 divided by s squared plus 2000s plus 5 multiplied by 10 power of 6. Okay, so the question asks you to evaluate the transfer function at omega equal to 1000 radian per second and omega equal to 3000 radian per second. Okay, so the transfer function is given. You just have to calculate the value for two different frequencies, which is 1000 radian per second and 3000 radian per second. Okay, so we look at the next page here. So now you first evaluate at omega equal to 1000, and you replace the value of s here with j omega. So omega in this case is 1000. Okay, so replace with j1000 for each occurrence of s. Okay, and solve for this. Okay, you can solve for this. You can check it back actually if there is any typo mistake here. Okay, so when you try to solve this, okay, this is the value that I get, which is j10 divide by 4 plus j2. Okay, so in order to solve this, you need to change it to the Fessor value. Okay, Fessor value of complex number. So rearrange for this, you will get 2.24 exponent j 63.4. Okay, so this is the value or the answer for the first question. Okay, hj 1000. Okay, so another solution is for omega equal to 3000. Again, you just have to change the value of s to j 3000. Okay, put in the value in the equation. Solve the equation by calculating or solving this multiplication. Okay, and for the division of the complex number here, you need to change it to the Fessor number. Okay, when you change it from the rectangular complex number to the Fessor number, then you can solve this division. You'll get 4.16 exponent negative j 33.7. So again, please check whether this value is correct or not. See another example. So this time we have a circuit with inductor and also resistor. And the transfer function here is defined as the voltage across resistor divided by V1, which is the V input. And now we need to find the frequency response of the system shown below at different frequency, which is 1000 pi for omega 1, 3000 pi for omega 2, 5000 pi for omega 3, and 7000 pi for omega 4. And given here the value of R, which is equal to 200 pi ohm, 200 pi ohm, and also L, which is equal to 0.1 H. So this one, the transfer function is not given, so you have to derive first the transfer function before you can put in the values of the omega. Okay, so to find the frequency response of the system, we need to evaluate the transfer function. We use the voltage division. Okay, so V2 divided by V1 is equal to R divided by R plus SL. Okay, R plus SL is the impedance for V1. So for S equal to J omega, you replace S here with J omega. Okay, it will become R divided by R plus J omega L okay, which is also equal to 1 divided by 1 plus j omega LR. This is when you have rearranged. If you don't want to leave it this way, it's okay. You can just use this formula here, not simple formula here, to put in the value. Okay, now the algebraic expression for the transfer function may be simplified here in the form by defining omega p divide is equal to r divided by L. Okay, R divided by L. So R is 200 pi ohm and L is 0.1 H. So the value here is 2000 pi. So we can say that omega P as corner frequency. So omega P here is defined by R over L. So it's up to you. If you don't want to do this, it's okay. You can just use the original transfer function that you have derived before. Okay, which is in terms of this. Okay. Okay, and then the phase angle is the arctangent. Okay, arctangent of omega divided by omega p. Okay, divided by square root of 1 plus omega divided by omega p squared. Okay, then when we got this, we can put in the value of omega 1, omega 2, omega 3, and omega 4. So these are all the calculations when we put the value of omega, as well as when we put the value of R and also L. Okay, so again, you can I'm not going to show it one by one, okay, because it is already here, it's already calculated for you. You can just check. Okay, you can just check the answer whether this is correct or not. So all these angles is in terms of degrees. It has the degrees actually. All right. So what you have to do is you put the value. Okay, first for j 1000 pi, and the next one is j 3000 pi, and the next one is j 5000 pi, and then j 7000 pi. So now you have already calculated the transfer function for different 4 frequencies. In case you don't understand, I'm going to repeat here again. Okay, let's go back from the previous slide. Okay, so now I hope you know already how to find the transfer function from these figures. Okay, from this figure, so the transfer function is given as the output voltage divided by the input voltage. So the output voltage here is the voltage across the resistor. Okay, so you find the voltage across resistor using voltage division. You can just put the impedance. So R divided by R plus SL. So you replace S here with J omega. Okay, J omega, and you rearrange so that it will become this form. So why do you need to rearrange actually? Because when we want to find the phase, okay, the phase and also the magnitude you can just square root everything here, and the phase here you will find by dividing arctangent of omega L divided by R divided by 1, right? So now you can also for this example, it define another form of corner frequency, which is omega p, which is equal to R divided by L. So why does the solution did this? Because it's going to ease your calculation. Okay, and the magnitude of the transfer function now is actually magnitude of transfer function is actually 1 divided by square root of 1 plus omega divided by omega p squared. So if you change omega p here, which is equal to R over L, you can get that omega divided by omega p is actually omega divided by R over L, which is L omega, which is omega L divided by R. Okay, the same equation that you obtained before, omega L divided by R. Okay, and in order to find the phase, okay, you just have to divide omega, you just have to find the arctangent of omega divided by omega p divided by 1, which is still the same as the omega divided by omega p. So the equation here here is actually the arctangent divided by the magnitude. Okay, because this is in a way how we can obtain both magnitude and also phase of the transfer function. Okay, so I hope you can understand this, how to obtain this equation. If you do not want to define this omega p, then it's fine. Okay, you can just calculate the arctangent of omega divided by r over L, and make sure when you want to find the arctangent, this part is already 1. Okay, the numerator is actually 1. Okay, and now if we see the answer here, we can see that at different frequency here, the magnitude here becomes lower and lower. So first, at the lowest frequency, which is 1000 pi, the magnitude here is 0.89, right? And as it goes to 3000 pi, the transfer function of the magnitude of the transfer function becomes lower, which is 0.55. And finally, at the highest frequency, which is Hj 7000 pi, the magnitude here has reduced to 0.27. Okay, so we can see that this transfer function is actually associated with a low pass filter because it passes low frequency but not the high ones, right? Frequency response plot. Okay, so for frequency response plots, it describes the output amplitude and the output phase of the network. So again, the frequency response plot describe the output amplitude and the output phase of the network. Generally, it is in the form of a filter function. So normally we are interested in plotting both the magnitude and the angle of a transfer function versus the angular frequency omega. Okay, so the output amplitude is actually Hj omega multiplied by the input amplitude, which is the gain, and the output phase is actually the input phase plus delta omega. Okay. We can use a semi-log scale to plot frequency response because, like I said before, range of frequency may span several orders of magnitude, and when we use the log scale, it can help to compress the data. It means that we can plot a larger frequency range. Okay, and also decibel scale relates to computational simplicity. And the gain magnitude here is usually expressed in decibel. So when we want to change in decibel, we define as 20 multiplied by log 10 Hj omega, which is the magnitude that we have found just now. Okay, the magnitude of the transfer function. But we have to calculate the log 10 of this magnitude multiplied by 20. Okay, so we use the Bode plot to simplify the frequency response plot, because when we plot the frequency response, normally we do not use any log scales. But when we use log scale, then it is called Bode plot. Okay, because it is tedious to plot the transfer function for the whole span of frequency range. Let's say you wanna plot from frequency as small as omega equal to 1, and then you want to plot a frequency as large as omega equal to 1000. So when you plot in normal graph, it will be a very, very big graph. So now when we use log scales, it can help to compress the data, and you can plot low and high frequency range in one graph. So for the frequency plot, I'm going to stop here because I'm going to continue to Bode plot in the next video lesson next week. Okay, so now we'll see at the exercise 1. This is the final equation in 2012 and 2013, semester 1. Figure 1 shows an linear time invariant system. It was found that the output of the system is equal to yt. Is yt equal to 30 cos t plus 90 degrees plus 0.3 cos 10t plus 10t plus 30 cos 1000 t minus 90 degrees. If the input is given as xt equal to 10 cos t plus 10 cos 10t plus 10 cos 1000 t. So it has different frequency, from omega equal to 1 to omega equal to 1000. Sketch the amplitude and phase frequency response of ht that fulfills the response given. Okay, so we need to, based on this output and also input equation, we need to sketch the amplitude and phase frequency response of HT. Okay, now we look at the solution. So we have here, okay, so let me draw it again for you. We have a linear time invariant system, which HT as the impulse response, XT as the input, and also YT as the output. So XT is equal to 10 cos t plus 10 cos 10t plus 10 cos 1000t. And for the YT, what we have here is 30 cos t plus 90 degrees plus 0.3 cos 10t plus 30 cos 1000 t minus 90 degrees. So now we need to plot the amplitude and phase frequency response of HT. So this is a very simple, because we can just take the we can just also use our knowledge of the Fourier transform plot of the frequency response. Okay, so for x omega, so we have omega in terms of rad per second. So now we plot in 1, also 10, and then 1000. Okay, so this is just sketch. So the scale need not be accurate, right? So for 1, the amplitude here is 10. Okay, actually for all. For 10, the amplitude is also 10. For 1000, the amplitude is also 10. Okay, so this is x omega. And for y omega, for phase, we need to plot the phase first. For x omega, we do not have any phase here. However, we just plot to show that it is 0 for 1, for 10, and also for 1000. Okay, this is 0. And for y omega is the frequency response of YT. Okay, so when we plot here, we have 1, we have 1, okay, and then we have 10, and we have 1000. Okay, so this is omega in rad over second. For 1, we have 30, so it will be higher, which is 30. And for 10, we have 0.3, lower. And another one for 1000, we have 30 as well. Okay, for the amplitude. And for the phase, here, we plot another one, which is the phase of y omega. So you can see here the solution is quite simple, as long as you know how to extract the information. For 1, we have 90, this is 1. We have 90 degrees phase. For 10, we have 0, because cos 10t does not have any phase to be added. And for the 1000, we have negative 90 degrees. Okay. Okay, however, here we have not actually answering the question. Okay, if you see the question, sketch the amplitude and phase frequency response of HT. This is the one that we need to sketch, the amplitude and phase frequency. Just now what we did is we sketched the input and also output frequency response because we want to know the relation. So you can see that from x omega to y omega, from 1 to 10, okay, from 1 to 10 or at 1, okay, the gain here is 3 because 10 multiplied by 30, multiplied by 3 is 30. So there is a gain by 3, okay, at omega equal to 1. So at omega equal to 10, there is a gain by 0.03 because 10 multiplied by 0.03 is 0.3. And another one is at omega equal to 1000. Raise again by 3 because 10 multiplied by 30 by 3 is 30. Okay. And then for the phase, we can see that phase at 1 and 1000 is 90 and also negative 90 degrees. And at 10 is 0 degrees. So from here, we can actually sketch the ideal response of the HT. Okay, because HT is the one that determine how the output will looks like based on the input. Okay, so again, HT will determine the relationship or will determine how the output will looks like when the input goes through it. Okay, so from here, I will put here, gain at omega equal to 1 rad over S is equal to 3. Okay, this is based on what I have discovered here just now. Gain at omega equal to 10 rad over S is 0.03 because when you multiply here, you multiply 10 with 0.03, you will get 0.3. Okay, and another one is gain at omega equal to 1000 rad over second is 3 because when you at omega equal to 1000, y omega is 30, x omega is 10. So 10 multiplied by 3 is 30. Okay, and for the phase at omega equal to 1 rad over S is 90 degrees. Phase at omega equal to 10 rad second is 0 degrees, and phase at omega equal to 1000 rad per second is negative 90 degrees. So from here we can plot the ideal response for the HT. So HT, when you change to frequency response, it becomes H omega. So for H omega here, okay, so we have 1, and then we have 10, and then we have 1000. Okay, so gain at omega equal to 1 is 3. So from 0 to 1, it is 3. Okay, from at omega equal to 10 is 0.03. So at 1, you go down to 0.03. Okay, this is just cash, so you does not need to be really accurate in terms of the sketching. Okay, in terms of the scale. And then at 1000, it will goes to 3 again. Okay, so sorry, this is too not accurate. Make a better straight line. Okay, and then it goes to 3 again. So this is what we call ideal response. Ideal response. Okay, because we put the the cutoff frequency sharp at the what you call it, the involved omega. Okay, so it's very sharp at the edges in terms of okay. So in terms of the phase, we have phase for Hj omega. Actually, you can put also H omega, and then from 0. Okay, and then we have 1, 10, and 1000 omega. So from 0 to 1, when omega equal to 1, we have 90 degrees. So we plot 90 degrees. Okay, and then at 10, it goes down to 0, and at 1000, it goes to negative 90 degrees at 1000. So it goes like this. So this is the phase, ideal phase response. Okay, so now you have answered the question for exercise number 1. Okay, so let us see exercise number 2 here. Given a network with a capacitor and also resistor, you need to find the transfer function. This is from the final 2011-2012 semester 1 So we have seen it before. However, sometimes the arrangements are different in terms of V out is a cross resistor or V out is a cross capacitor and so on. So we still have to find the transfer function one by one by using our knowledge to find the transfer function. Okay, so find the transfer function V out divided by V in. Write the expression for magnitude and phase. Okay, at the steady state when sigma equal to 0, and then suppose the values is given of capacitor is given as this one and this one. You have to calculate the transfer function for the two input signal when V1 is equal to this value and also V2 is equal to this value. Okay, so it means that once we found the transfer function, we chip in the value here and we calculate the transfer function based on the given V1 and V2 signals. Okay, so both V1 and V2 is actually the V in signals. And calculate the amplitude and phase of the output signal for the two input signals. Okay, so we want to solve this one by one. Okay, so again for the transfer function, it's actually V out divided by V in. So remember the diagram, we have, see here, we have R and we have V out here and we have V in here. Okay, so for using the voltage division, okay, we can get R divided by R plus 1SC. So please ignore my background. There's a cow outside of my house. I'm in my village right now. There's a cow outside of my house. Keep on moving. Okay, alright. So V out is actually voltage division R divided by R plus 1SC. So rearrange again. R divided by SRC plus 1 divided by SC. Okay, so here we will get SRC divided by 1 plus SRC. Okay, and this is the transfer function. And number 2, we need to find the, if you go back to the equation, the expression of magnitude, or in other words the expression of a transfer function in terms of Hj omega. So we just have to change to S to J omega, because at steady state S equal to sigma plus J omega and sigma here is equal to 0. So Hj omega is equal to, when we use this equation, J omega RC divided by 1 plus J omega RC. Simplify this further. This you can become R divided by R plus 1 J omega C. So if you want to leave 1 at the numerator, become 1 divided by 1 plus 1 divided by J omega RC. Okay, so now we want to find H J omega. Okay, so actually divide by the square root of 1 plus 1 plus omega C. Okay, got for the magnitude. And for the phase, omega is actually negative tangent 1 over omega C, 1 over omega RC divided by 1. So 1 over omega RC. Okay, so this is the magnitude and also phase of this transfer function. Back to question 3. Okay, you need to find the values of resistor and you need to find the transfer function for these two input signals with the resistor and capacitor values given and also V1 and V2 values given. Okay, so let me put it here. Sorry for the red color pen. Okay, so R here is equal to 0.1 ohm, C equal to 1 divided by 100 pi farad, and V1t is actually equal to 100 cos 2 pi multiplied by 500t, and V2t is equal to 100 cos 2 pi multiplied by 5000t. Okay, so from question 2, we can get the transfer function in terms of omega, which is equal to r divided by r minus r divided by r plus 1 divided by j omega c. Okay, so this is actually equal to r divided by r minus j omega, minus j divided by omega c. Okay, sorry for the messy. So now, okay, we just put in the value. Okay, we just put in the value according to the value given. So r is 0.1 divided by 0.1 minus j. C is given as 1 divided by 100 pi. So this one, we can put 100 pi here at the numerator. Okay, divided by omega. So this omega we change for using 500 and also 500t. Now for omega equal to 2 pi times 500, okay, we can get h j 2 pi 500 equal to, we put the value, okay, 0.1 divided by 0.1 j 100 pi, sorry, this is minus j 100 pi divided by, this is the division, divided by pi multiplied by 500. Okay, so you rearrange, you get 0.1 divided by 0.1 minus j 0.1. Okay, so find the solve this using the factor number, change it to the factor number at the denominator here. So you get 0.7071 45 degrees. Okay, so use another frequency 2 pi 5000, which is equal to, when you put in the value, 0.1 minus divide by 0.1 minus j 0.01. This one you will get 0.995 5.71 degrees. Can you check this again? Because I don't have the calculator, so I'm using my calculator. I hope it's correct. Okay, so now you already answered question number 1 and number 2. So to find the answer for question number 4, which is the amplitude and phase for two output signals, okay, so we use the equation here, okay, we use this equation in which we already have a hj omega. So we multiply by the input amplitude to get the output amplitude, and for the output phase, we just have to add delta omega, which we obtain from the hj omega, and then plus the input phase. Okay, so in order to do that, for question number 4, so VO omega, which is the output amplitude, is equal to hj omega multiplied by V1 omega. Okay, so for omega equal to 2 pi, so omega equal to 2 pi 500, VO omega equal to, this is 0.7071 multiplied by V1 omega is given as 100 here. Okay, 100. So multiply by 100. So we will get 70.71 volt. And for the delta V naught omega, there is no phase here at the V input. So it's actually 0 plus 45 degrees. So this is 45 degrees. So we know that now VO1 omega is equal to 7.71 volt. and 5 degrees. Okay, so this is for V input 1. So for V input 2, which have omega equal to 2 pi 5000. Okay, VO2 omega, so this is for 1, sorry, this is for 1, equal to Hj omega multiplied by V2 omega. So now, you check again, please check this again, because I have two values here. It's either 0.1005 or 0.995. So I'm not really sure which one I have calculated, so you can check again. So let's say I use this 0.995 multiplied by 100. Sorry, multiply by 100. So 1, 2. So here we'll get 99.54. And for the phase, it maintains the 5.71 because it doesn't have any input phase here. Phase with 5.71 degrees, and hence we got VO2 omega equal to 99.5 volt and 5.71 degrees. Okay, so now you answered both questions. So again, please check if there is any typo, if there is any mistake that I have done in the calculation. Okay, and in the next video lesson, which is the next week, perhaps in we are gonna meet face-to-face video conferencing. So I'm gonna show you how to plot the Bode plot. Okay, it's gonna be another intense video or intense session, because the Bode plot is actually very important, and this chapter is quite important because it is a compulsory question during the final exam. Okay, you do not have any option to answer or not question for chapter 5. You will have to answer question for chapter 5. Okay, so until then, thank you very much for listening to my video. Don't forget to scan your attendance after you finish watching this video.